Good, everybody. My name is Petronilo Martin-Iglesias. I work at Tech in the Netherlands as a microwave engineer. I would like to talk about the use of stereolithography for the manufacturing of microwave components. AM theory is defined as an additive manufacturing process in which liquid photopolymer in a vat is selectively cured by light-activated polymers. We have seen the presentation from Roberto. The classifications done as ASTM, vat is one of the 6, 7 included there. But inside the vat itself, depending on the process itself, we can find names like stereolithography, familiar known. These are light processing, continuous direct light processing. But just to explain the concept, maybe we can start with the LA, which is the picture that is included in this presentation, where a layer is drawing on the surface of the liquid one of the layers. After that, the building platform moves down, and the sweeper places another layer of material. Later, the laser starts doing another layer of the structure, and at the end of the processes, the part needs to be removed, cleaned, post-processed, and is finalized. The material that can be used for this process are, I just listed here 4. So for propylene, polyethylene, polycarbonate, ABS, or ceramic. For vat is similar than the process that has so we start with a CAD design. In the CAD design, we move to an STL design. We perform the sliding with the software. And we can go for printing. So after the printing, of course, we need to remove the support, if any, and to perform post-processing. One of the important part of this manufacturing process is without the of high temperatures, so we don't have any stress, mechanical stress. We have good accuracy in police, good cost, and it's providing pretty good roughness. This for the manufacturing of ceramic parts, the process changes a bit. So the first part, as we can see in this picture provided by Slim, is pretty similar. So we go from the design through a STL file, sliding, and the printing. But from there, we need to do cleaning, and the photosensible page is with ceramic material. What we need to do is to do the printing and sintering of the final part to have enough hardness. To show the value, the performance we can achieve, to remark how good can be the surface finishing, which makes this process very suitable for RF components, where one of our main requirements is accuracy. Also, we need to consider that for some specific manufacturing processes, for example, one is called TPP, to photon polymerization, the resolution can be much better. You can go to 100 nanometer. Of course, the size of the component that you can print will be much lower. But this kind of manufacturing process, to set this kind of manufacturing processes, we need to consider all the parameters. We need to consider, we have talked already about accuracy, resolution, which SLA, for example, is able to provide, cost, high speed for the printing. That's a wide range of material. However, we cannot print any metal material, so this is one of the first limitations. And the mechanical properties of this kind of materials need to be considered. So what I'm suggesting here is that when we're using this Vat Photo-polymerization process, we consider the end-to-end process. And we need to consider as well that the SLA can be used as one step in the whole manufacturing process. I mean, it doesn't need to be used only for the final part. We can print, for example, a mandrel. From the mandrel, one is plated for the electrical conductivity and for the mechanical properties. The mandrel can be removed. So, SLA, for example, can be enabling for RF components just for as a printer of part that will be removed later on. Now go through some of the examples that have been included in the special issue of the IEEE. First one was included in the paper from Jeff Maas. It's for a 2 to 12 gigahertz double reach horn antenna. You can see here, well, the paper is called Laser-Based Layer-by-Layer Polymer Stereolithography for High-Frequency Applications. The thing has been done in polymer and has been plated with a conductive ink. And if the conductivity wants to be improved, on top of this conductive ink, electroplating can be performed. The benefit of this kind of manufacturing process, you can go for pretty big parts. In this case, we can see that it's 121 millimeters by 69 millimeters and a length of 88. Of course, in this case, the electroplating of copper was not considered, so the conductivity is much lower, one order of magnitude lower than in the case of copper. In this case, the residue loss was better than 9 dB from 212. The antenna efficiency was around 87. If considering the conductivity of the copper, if the plating is done, the efficiency can go till 95%. Another example where the complexity was one of the main issues included in this paper from Joana Silva, EPFL, where this small antenna was manufactured by Swiss 212. It's a dual band low density antenna, which is pretty suitable for array antennas due to the small size and the very low weight. In this paper, it's described that the weight of this small antenna is 0.5 grams. This can be very suitable for example, LEO satellites, where due to the small platform in satellite, we need to have a very tight accommodation of the antenna elements. Talking about this manufacturing, if we look at the complexities, it has been manufactured in a single part. If we consider a traditional manufacturing, that needs to be plated in several parts and then plated. In this case, the plating was done with SLA, and then the polysurface were treated, then plated with copper. For the performance are showing the residue loss that is better than 10 dB and can be improved in the future if we consider the beamforming network. And we see the pattern, the reaction pattern, and the comparison with the simulations. We move to the next example. This is a pretty good example about the integration of functions. In this case, we are integrating power divider, 80 degrees waveguide twist, waveguide bends, meter bends, and the conical antenna in a single part. The part has been the same in the previous one, has been printed by the Swiss 212 and coated based on a process that is being patented at the moment. And the residue loss from 26 to 40 is most of the time below 30 degrees. The gain, we can see the comparison for the gain and for the radiation pattern and the cross polar. The radiation pattern is at 33.25 for the 2x2 array antenna, and how well it matches. The very last example, this vacuum has been performed with ceramic material, in this case for zirconia, and is a clear example how the challenge, the complexity of the dielectric part has been solved with 3D printing. In this case, the idea of the solution is to move the filter in a range of 22.2% without changing design, of course. It has been shown that just turning these three parts, the author is able to move the filter in this range, keeping a pretty good Q factor. The example of the use of LA, I remark that one of the challenges in this case, in most of the cases, not in this one specifically, in most of the cases, the plating of the surface. So now I pass the floor to Bashar and to Roberto again. Thank you very much.